actually that. Very, very good guess. You guys are so smart. This is awesome. Okay, so what Mat2Vec does is it takes in all of these abstracts from these scientific papers on a specific topic. For them, it was thermoelectric materials. And these are papers from like the 1800s through now. And what it did is it took words, it took terms like chemical elements or materials that were closely associated with the word thermoelectric, but they did not take place in a thermoelectric materials paper. So it was like, these materials are likely thermoelectric, but no one has realized it yet, and they haven't been patented yet. So
they were looking at for terms that were not in thermoelectrically geared papers, and trying to see if they're finding it in other non-related areas.
yes, exactly.
Wow, and that still it works. And you can use it for what? What would you use it for?
Well, when I first heard about this, I was like, this is cool. I want to use it to figure out how to travel to other stars. You know, use artificial intelligence to figure out interstellar space travel. As I researched the model more, I don't think it would be applicable for that, because there aren't really a lot of scientific papers on how to do that. You know, there aren't a lot of credible scientific papers. There's like a lot of theory, but nobody's ever done it. So they say that the Mat2Vec can get you 5 to 8 years ahead of where we are right now. And I don't think we're 5 to 8 years ahead, you know.
So it gives you just a list of papers, really?
No, it gives you a list of terms, I think. I'm not really sure what the output is. But yeah, Mike, if you wanted to train that on papers, medical papers about specific molecules or about specific drugs, what it could do is it could tell you this particular molecule is associated with, let's say, diabetes, but it has not appeared in a diabetes paper, and it's probably not patented as a diabetes drug. So
that's what I'm looking for.
Diabetes drugs?
No, actually, yeah. I mean, any over-the-counter marketplace. That's where I'm at. I'm never going to be a part of the pharmaceutical industry, but you know, when CBD came out, all of its buddies, all of its compounds that can, you know, work in concert or whatever you want to say, with just any nutrients, really, any plant-based extracts, things like that, for product formulation for specific purposes.
That's actually a really good idea. You could also use this to find purposes for CBD that have not been discovered yet. Like you could figure out CBD is really good for treating gout or Hamertoe syndrome or things like that. So lots of potential.
What is that website you're talking about? Mat2?
MAT2VEC.
2 the number 2?
Yes.
CED?
VEC.
VEC.
So I think you were absolutely right. Mat2Vec is materials 2 vectors. The original was called Word2Vec or Word2 vectors, but they just used it for materials. Okay. So now we're going to talk about deep reinforcement learning, which I believe is going to be one of the most important types of artificial intelligence. And the reason why is because it deals with machine behavior. Okay, so we already talked about artificial intelligence and machine learning. There are many types of machine learning. Deep learning, we talked about that too. A computer uses an artificial network to approximate a function by matching input and output data. Okay, reinforcement learning is a type of deep learning, right? So we've got artificial intelligence, then machine learning, then deep learning, and then reinforcement learning. Deep learning is, you know, the artificial brain. It's called deep because, you know, how we saw there were layers of neurons? It works best when there are a lot of layers as opposed to one layer with a ton of neurons in it. That's the only reason why it's called deep learning. So now you guys know. Okay, so reinforcement learning is teaching a computer to accomplish a goal using rewards and punishment.
Kind of a funny concept.
I know, right? It's very weird to think about punishing a computer. Okay, so I'm going to go through the why, the how, and the future of reinforcement learning. Okay, first we're going to talk about the why before we even get into how it works. So a couple years ago, a startup called DeepMind created an artificial intelligence that beat the world's champion at a board game called Go. You'll see it right here. It's little black and white pieces. In 1997, I believe, 97 or 98, Deep Blue beat the world's best chess player. And people just said, oh, well, you know, chess, whatever, you know, it's cool, but, you know, he couldn't beat Go. Go is much more nuanced. So what DeepMind, this company, did is they programmed thousands of real human games of Go into a computer. And the computer learned from those games, and it beat the world's best Go player. So that was a pretty big breakthrough, but the next thing was even cooler. This is AlphaZero, which was by the same company. This one was called AlphaGo. This one is called AlphaZero. It's called AlphaZero because it is not trained on any data. Humans had zero, or any real data. Humans had zero input into this. It was not taught how humans play games. What it did was it played millions of games against itself, and that was how it learned. It had never seen a human play Go. It had no idea how the human played Go, but it was way better than the original. It was way better than AlphaGo, and it beat it 100 times in a row, even though it was not trained on human games. It had never played against a human before.
It just had the rules put in.
Not even that. Well, okay, yeah, I think the rules were put in, and then it was taught how to play. Okay, so the reason why this is so cool is we talked about how messy data is, right? There are bad numbers everywhere, and you got to clean up the rows. Sometimes somebody will misspell things. And one of the hardest parts about deep learning is you have to have an enormous data set. You have to have like 20 to 50,000 records for it to be useful, right? And sometimes you can't find that, right? Or sometimes it's really, really hard to find that. Google has a data set search engine, which is great, but what if you want to do a problem that's kind of obscure? What if you want to classify hair types just from a hair strand? You're going to have to take photos individually of 50,000 little hairs, and that's not very fun. And the reason why synthetic data, or a computer playing against itself, is so cool is because you don't need to clean it. It wasn't made by a human, it was made by a computer, so it's perfect automatically. It's quickly generated. You don't have to take photos of 50,000 hairs. The computer generates it all very quickly in its own mind. And it's easy to generate. You just enter a command, and it applies to the real world. You can take a simulation of the real world, train a computer in it, and then you can make a robot, and that robot can move around in the real world. So cool. It's really hard to do that. I've been told by robotics experts it's very hard to do that, but in the future I don't think it will be. Okay, this is a really, really cool thing. OpenAI is this nonprofit that develops artificial intelligence. And what they did is they trained a robot to solve a Rubik's Cube. And once again, they didn't train it in real life because that would have taken forever. It would have taken millions of iterations for it to learn. So instead, they trained it in a computer using simulations. They had hundreds of this simulated hand in a simulation going at the same time, and the one model was learning from the experience of every one of those hands. So in a computer, they trained it for millions of years because they trained it with, dozens of hands, and then they sped it up. So the computer was learning all these things at the same time, and so it only took a couple of weeks in real time, but it was to the computer, it was millions of years of training. Then they put that model into the real robot hand, and it worked. Okay, this one's really cool. I like this one a lot. So in 2017, OpenAI created an AI that deleted pro Dota players. If you don't know what Dota is, it's a video game where you sort of command your troops around an arena and they fight each other. It's a very, very popular game, and it's all over the internet, and there are world championships. People win millions of dollars.
What does Dota stand for?
Defense of the Ancients.
Defense of the Ancients?
Yeah, it was just this game that blew up. Millions of people all over the world love it. This is the top ranked team in the world right here. Their name is OG. This, again, was not trained against humans. It never watched a human game. It was only trained against itself. It played millions of games against itself, the computer was controlling these guys and it was controlling these guys. It was attacking, and it just learned how to defend and how to fight. So it was trained against itself, and they won against the world's best players. And one of the interesting things is, after this went live on TV and all these people were, going crazy about it, a lot of people commented on the video. They said, "Oh, you guys made all these mistakes. You made this mistake. You made this mistake. I could have beaten that AI easily." So what OpenAI did is they said, "You know what? We're going to let anybody play against this. For a week, we're going to let anybody play who wants to against our AI." The AI had a 99.4% win rate against anybody who tried to beat it. So I watched the video of this, and the announcers who know what they're talking about as far as this game goes said that one of the main strategies of the AI is it would rush into battle, right? And then at the precise moment when its health bar was so low that it was going to die, it would run away. And then people couldn't catch it, right? And to do that kind of calculation, you would have to do it within microseconds of the exact point in time when you would have to do it. So they wouldn't die, they would run away and they would go recharge their health. Whereas the humans, they can't make decisions that quickly, so they would just die, right? They couldn't know when to run away. So it was pretty funny and probably a little bit infuriating for them to watch.
Oh, so they played like a game of odds almost, where they would go in and if they won, they would stay, and if they lost, they would leave.
Yeah, and then they would leave and they would go heal and then run back in.
Did ever even kill them at all?
It was really frustrating to watch because they had such a hard time killing them, because like they would start attacking and then the enemy would go down to like a third health and then start running away, and then the humans would start running after them and they were out of range already.
Yeah.
So we just chase them across the map and they couldn't get them. Also, the AI could cast like compatible spells within fractions of a second. Like it could cast 3 spells like all at once, like a shield and then lightning that would go over it and stuff. And people can't think that fast. So it was really fun to watch.
Well, the interesting story would be the 0.6% that beat the.
Yeah, bragging rights for sure. Yeah. And these guys were not happy. Like this, you can see this guy's face. He was not happy about losing because they trained.
It's his empire.
Yeah, he trained for a long time on that. Okay, so now we're going to talk about how this works. Okay, so the idea for reinforcement learning came from rats in a maze. You start right here, you put a rat at the beginning of the maze, and you put food at the end, right? So the mouse runs through the maze, the rat, and then he finds the way to the food, he eats it. Then you start him back again at the beginning, he runs through it, and he goes a little faster, and then a little faster, and a little faster, right? Until he's an expert at the maze. So, so here we're going to do an example. I'm going to close my eyes, and I want you to guide me to Mike using only claps. A clap is a reward to me. So if I get closer to Mike, I want you to clap, and if I get farther away from Mike, I want you to just do nothing. Okay? Ready?
Oh, wait a minute.
Well, theoretically, you're closer. You are closer.
I was? Oh. Oh, well,
You
yeah.
avoided an obstacle.
Oh, that's true.
Which is why I clapped, but I didn't realize that I was supposed
All right.
to only do it if you're closer to me.
There are too many wires here, and there's a chair in front of me. So I'm not going to go any further with this experiment, but you guys get the idea.
Yeah.
You can move somebody, you can give somebody directions using only a reward. And the reason why we do this, instead of just telling the computer what to do, is because we want it to learn on its own. Sometimes computers can come up with better solutions than we can. So we do a hands-off approach and we say, if you accomplish this task, I will give you a reward, and that's it. And so the computer behaves randomly, but it learns from its own mistakes until it can get that reward. And the reason why this is effective is because a computer can perform random experiments a lot faster than a human can. This is kind of how life goes. Once you graduate from college, you have no idea what you're going to do. At least I didn't. I experimented with a bunch of different careers, trying this, trying that. It was just random. And then I found one that I like. And so I'm staying in it. All right.
What is was there a term, the thing about AlphaZero not being trained with any historical actual games, but just experimenting. What is it? What's the terminology for zero or for
Self-play
self-play?
or synthetic data.
Synthetic data. Okay.
And there are just so many advantages to synthetic data. I was blown away when I found out that it can apply to the real world.
But you have to also have to create the environment for it to learn in.
Yeah, actually for the hand, the environments that it learns in, the simulations, are usually not very accurate to real life. So for the hand, what they did is they trained it in hundreds of different environments with slightly different parameters so that it would generalize to anything, and then they put it in real life and it was able to generalize to that. Okay, so there are a couple pieces of reinforcement learning. There's the agent, which is me. Remember we did the experiment where I was walking around. I'm the agent. And then there's the goal, which is Mike. Then there's the reward, which is the claps, right? You guys were clapping. You guys were giving me the reward. All right? And the environment was this room. I was walking forward, right? And the state is the tile that I'm standing on. Like, I'm on this tile, I'm in this state. Go right here, I'm in a different state. Go forward, I'm in this state, right? So that's reinforcement learning, just those few pieces. And in each state, I can take a specific number of actions, right? I can go forward, I can go backward, left, right, etc. Whatever tile I'm on, I can move forward, I can move backward, etc. In reinforcement learning, you have to define what actions you can take. Like for instance, if we were playing a video game, video games have limited numbers of controls, right? You can go forward, you can go backward, you can shoot, you can change a weapon, you can sprint, you can open a door, right? Those are all actions that you can take in a video game. And so for reinforcement learning, you have to define which actions you can take. All right? And it's a limited number of actions. Okay, and a reward function is the total rewards over the entire episode. So like if I had counted up how many times you guys clapped for me, right? That total would be the reward function. And it's what we're trying to maximize. Okay, now imagine yourself, you fall asleep, you drift off to sleep, and then you wake up and you're on a chessboard. Really weird, you're on a chessboard. You don't know what you're doing here, you want to get home, so you start moving. You move left, nothing happens. You move left again, nothing happens. You move up, and all of a sudden from this tower, a piece of cake gets launched and it lands right in the square where you are. You're a little bit weirded out by this, but you try to eat the cake and you're like, oh my gosh, that's the best cake I've ever had. That's amazing. I want some more cake, but I also want to try to escape. So you move up, you get another piece of cake. Awesome. This is so cool. Whoever's in this tower is launching pieces of cake at you. And so you get more and more and more. Oh, this is amazing. Oh, what just happened? Why don't I get any cake anymore? You kind of start to freak out. You're like, what? The last two spaces, I didn't get any cake, and I'm not getting any cake. I want cake. So you move to the right. Oh, cake is back. Yes, best life ever. This is amazing. I get cake. Uh-oh. Why did my cake stop? I don't understand. Where's my cake? Oh, there we go. Cake, cake, cake. Oh, no more cake. Okay, now we're back there. So, as you can see, this little old man in the tower, he was throwing you pieces of cake every time you moved to a place that he wanted you to move, right? So this is, again, that reward function driving you to other places. And you wake up, and the only thing that you remember is the moves that you took. This is your policy. It's called the policy because it's the actions that you take in specific scenarios. Like I've said this before, I went to Walmart and I tried to return a potato that I had already eaten. And Walmart said, it is not our policy to accept regurgitated food in return for money. And I threw up the potato into my hands and I said, look, I've got it right here. I'll give it back to you. And they said no. So Walmart's goal is to earn money, right? And so in specific situations where somebody tries to return a regurgitated potato or a regurgitato, as I call them, they say no because they want to make money, right? That is their policy. Just like here, our goal is to maximize our reward, get the most cake, and so our policy is the actions that we take toward that goal. And it's also kind of like a history of your actions. Okay, so Let's say we're in a different situation. Similar, but different. We only have cake at the exit. We don't get any other clues. We only get the cake right here. So let's pretend like we cannot see that cake. But lucky for us, it is hot and it is freshly baked. What is another way that we could tell where the cake is?
Smell.
Smell. Very good. Perfect. So let's say that smell radiates out like this, and let's put a number for the smell. Let's say where the cake is, smell is 10, 9, 8, 7, 6, radiates out, right? That's where the smell is. That's the intensity of the smell. So what we want to do is we always want to be going from a lower smell state to a higher smell state, right? Because if we're doing that, we're getting closer to the cake, right? So we go up to 6, and then we have a choice. We can go left or we can go up. I'm going to go left here. And then we want to go to a higher smell state. We're in 7, so we don't want to go to 7. We definitely don't want to go to 6. We want to go to 8, then 9, then we want to go to 10, right? And how you figure out what this smell thing is you calculate it. You calculate expected values of this state. You kind of have to know everything about the state to do this. It's not deep learning for this one, but it's kind of similar. So we can, actually, here's another thing to notice. This is the path that we used right now. You could use a different path. You could use another path, just as long as you are going up the scale and trying to get to the goal. Okay, this is cool. Greed versus exploration. This is a very important topic in machine learning. You might say, okay, well, why, if the machine finds a reward, if there are 2 rewards in a place, why wouldn't the machine get stuck on the first one that it sees? Why wouldn't it just stay there? And the answer is greed versus exploration. So let's pretend you are a baboon and there is a tree and you are on the African savanna. You shake that tree, and every 5 minutes that you shake that tree, a bug falls out and you get to eat it. So here's the question. Do you stay there shaking that tree, for 5 minutes and getting a bug? Do you do that all day? Or do you want to go and see if maybe there's a better tree? Maybe a bigger tree with more bugs in it? Do you want to go and shake this tree? Maybe you find this tree and there's a bigger bug and also another bug, and every time you shake it, every 5 minutes, big bug and a small bug pops out. This one would be better than the last one. So how do we account for that with computers? So it's epsilon. Epsilon is a fancy word for saying how much of the time you're going to explore and learn about new things, and how much of the time you're just going to be greedy and capitalize on what you already know. So let's say epsilon 20%, what 20% of the time I'll go explore, and the rest of the time I'll exploit what I already know. So this is a way of finding better and better strategies or better and better policies. So the gorilla or the baboon might stay at the first tree. He'll stay here at this first tree 80% of the time, and he'll shake it and get the bug. And then 20% of the time he says, okay, I'm going to leave this tree and I'm going to find other trees. I'm going to see what happens. So maybe he finds trees that don't have any bugs, and he comes back to this one for the 80%. The next time he goes out 20% of the time, he shakes other trees, doesn't find any. Maybe like the third time he goes out, he finds this one. This one's a great tree, right? This one is the new exploit tree. This one is the new greedy tree. If he hadn't explored, he would never have found this tree. But now this one's better than the last one, so he spends 80% of his time here now, and then 20% of his time still exploring, looking for a better tree. Okay. All right. So deep reinforcement learning. This is a photo of an artificial neural network right here. What you do is you put in, we already talked about this. You got inputs and you map them to outputs. And the goal with a neural network is to maximize accuracy. Remember, we talked about root mean squared error and the area under the curve. With the confusion matrix with false negatives, false positives, etc. You want to maximize your accuracy. But with the deep reinforcement learning algorithm, what you want to do is the input is your state and the environment. Your output is your action, and you want to maximize the reward. So let's say my state is right here, And I get more rewards as I move towards Mike. So this is the state I'm in right now. Which direction do I want to move if I want to get closer to Mike? I want to move forward, right? That brings me closer to Mike. And so that maximizes rewards. I'm in this state. I choose the action in this state that will maximize my reward, right? So just like a deep learning or an artificial neural network maps inputs to outputs and creates an equation, it's the same for reinforcement learning. Okay. Okay, so let's take a look at this. As the agent gets closer to the target, its rewards increase. So given that we are using a neural network and we're trying to maximize the rewards, which way, and the agent is in this state, which way is the agent going to move? Which action should this agent take? Yes, perfect. Moving right, because it is trying to maximize its rewards, and the closer it gets to the target, the greater its rewards go. Okay, so a little bit more complex than a chessboard is an Atari game. The state is the entire screen. The state is where the aliens are. The state is your lives, the score, how many of these pillars you have left, where your spaceship is, and the actions that you can choose are left or right or pew 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 when you shoot a laser at the bad guys. So deep neural network takes a look at this screenshot. It just looks at the pixels, right? And it figures out what the state is. Then it chooses an action based on the state. Like with Space Invaders, you're supposed to shoot at all the bad guys. So if there's still bad guys there, then your spaceship is probably going to shoot at them. That's probably what the neural network says. It shoots, and then it acts, creates an action. It acts on the environment or the state, and then the environment changes, right? It could be due to what the neural network's action was, or it could be just due to the environment. These guys move. Whenever these guys move, the environment changes, the state changes, etc. But also, this guy fired, he just blew up an alien, right? So the state has changed. There's one less alien. So now we repeat the whole thing over again. This guy takes a look at the state, he chooses an action, the action changes the environment. And it's just a loop over and over and over again, right? And then we try to maximize the rewards. It plays the same game over and over and over again, trying to maximize the score up here, trying to get the highest possible score it can. And it does that by doing random actions and seeing which ones give it the best score. All right?
Yeah. So it doesn't have any real understanding of what's happening. It's really just, how long does it take to train that the algorithm that gives you the action?
That's a good question. I don't know for this one. I downloaded it to my computer and I used it, but I used a pre-trained model. So I don't really know how long it takes. Okay, you can also use it on three-dimensional games. Like for instance, this is a blue guy who's trying to push the cube across this line. And this is the first time it's ever tried it, so it's terrible, right? It is just, you know, moving around like this, doing random motions, right? But it gets a reward once it pushes the cube across that line, so it eventually learns. So this is after many iterations. I think it's like 200. I think this was after like 200 or something like that. But yeah, so it eventually learns, oh, if I push it over here, then I get a reward, right? And so it creates its own actions leading up to that. Okay. All right, so.
Thank you very much.
All right, you taking off, Mike?
Yeah, I have dinner again tonight.
Okay. Oh, you can see you, Mike. Do you know what time is it?
4 till, 10 till,
Till what?
5 till.
Till 4?
Yeah.
Okay. All right. So these are my predictions for where reinforcement learning is headed. So I think reinforcement learning will be used in military strategy because it is the highest risk game, and this technology can beat any human at a game. So this is like the most important area. So let's see, you've got two armies. One is given their strategy by an artificial intelligence that uses reinforcement learning, and one is just normal humans using their experience. The reinforcement learning algorithm has millions of years of experience, whereas the other one, they've got maybe 30 years of experience if they're a career general. Just like in the example we showed with the video game, they're likely to have a 99.4% chance of winning. So it's really important to use this technology where we can. Also, I think military units will be controlled by artificial intelligence. This is actually a jet fighter that is controlled by AI. They've shown that AI planes were able to beat humans in flight simulators. And also, airplanes have forces, or airplanes exert forces on the human body that are unhealthy for it. Like if you go into a big swoop, you can get knocked out. You can lose all the blood in your brain. But artificial intelligence does not have that problem at all. It can be much more agile, much faster. And computers think way faster than humans can. Like the human reaction time is around a quarter of a second. Computers can think millions of thoughts in a single second. A computer can identify a foe and destroy it before the foe even has had time to think.
What, are you familiar with any of the current state of that development? I guess they had something back in World War II, or the end of World War II.
The Enigma machine?
Unmanned aircrafts to deliver bombs.
Really?
Yeah.
Like the V2 rockets and stuff?
Well, maybe, but these were aircrafts, I believe, that would deliver bombs and come back.
Uh-huh.
Really?
Yeah, but it says that they never really would be remotely controlled.
Really?
Mm-hmm.
I don't know how they would do that. That's really interesting.
Like a drone.
Yeah.
Basically,
It wasn't, what would be the expression for something that was controlled just by itself rather than from somebody far away?
Yeah, autonomous.
Autonomous, yes.
Yes.
And politically, if there weren't pilots being shot down and killed, the country would be much more willing to go to war
Yeah.
because of the public relations.
Yeah, it's true. I mean, that's the whole thing behind, Iraq and Afghanistan. They fly drones that are so high nobody can see them.
And it seems like it's not that far away that you could have completely automated fighter jets fighting against human pilots, and they couldn't do the things that the automated autonomous jets could do.
Actually, so the U.S. military had formed a contract with Google. Google was going to help train drones to be autonomous. They were going to help them use aerial photos to identify people on the ground. And a bunch of Google employees found out about it.
That's what they were.
And they walked out because they don't want to be a part of the American military. Also because Google was building a search engine for China, and Google employees said, we don't want to work with this because they're going to restrict freedom of speech. Okay, so we talked about how AI will control strategy and AI can control units. So if we bring those two together and we turn all of our US military over to an artificial intelligence, that is the plot of this movie. So I don't think this is going to happen. Artificial intelligence is not intelligent enough yet to make decisions like killing all humans. Like I said, it can only do like one thing. It can only do what you program it to do. So if AI does something scary, then I'll let you guys know. But so far, I'm not worried about anything. All right, so that is the end of the talk, and thank you guys for coming. This is the end of the lecture, but I will show you guys the beautiful image generation software that I mentioned.